solve real problems. It is used for improving efficiency of many business verticals, and it is used for solving human-centered issues, and so on. So as we can see, almost every decade there is a new generation of wireless systems that comes to address certain number of requirements of the decade, and every 20 years there is a new market value that is created. And one particular thing that actually shapes this era, other than any other time, is the Internet of Things, the rise of Internet of Things, where we have billions on billions of devices that are interconnected, and they have communication capabilities and sensing capabilities. They are used everywhere, in the automotive industry, consumer industry, industrial applications, and so on. So to address these, to serve these massive number of interconnections of devices, we need to design techniques that, that can handle this. And this poses certain requirements. The requirements have been the same through all eras of wireless communications, but they get by time, in a specific time, some requirements get more important. Especially in this era, in the era of IoT and Internet of Things and 6G, we will have to serve many requirements at the same time, simultaneously, which is sometimes a challenging task, and that's why we need to design new techniques for this. One of the main requirements that is posed in this regard is a spectral efficiency requirement, or the capacity, where we have a massive number of interconnections that need to be served. And that's why we should have techniques that can do more with less. That means that we have a restricted spectrum allocated for wireless communications, and thus we need to use this spectrum very wisely, effectively. And this is a spectral efficiency requirement. Another thing that is important regarding the spectral efficiency requirement is that we have applications that rise day by day. We have a lot of applications in our mobile phones and everywhere, and that's why all the devices are data hungry, and thus we need also to address these hunger per device. So these are the 2 points concerning spectral efficiency. Another important concern in the design of new communication systems for the future is the wireless security, and this is a problem posed now rather than at any time, because now we have a lot of connections, and this is very risky due to the broadcast nature of the wireless channel. And that's why the techniques we design now should take these into account. Another important requirement, especially for IoT devices, Internet of Things applications where the processing is restricted with the battery life and so on, we need to design schemes with low complexity and low latency as well, especially in emergency applications where latency is an important thing. The transmission reliability is also important, a very important requirement, where any system that is designed, any wireless system that is designed should provide a sufficient level of transmission reliability. In some cases, ultra reliability is needed. Also, power consumption and energy efficiency is one of the main requirements posed now, especially in the IoT, for IoT devices, because they are limited with their battery life and processing restricted. So in this regard, having discussed the overview and the problems we have to address, we developed in this regard some designs that solve some of these issues. We developed 3 designs in this thesis. We developed first a scheme called multi-user auxiliary signal superposition transmission, which is which integrates 2 directions of research: physical layer security for addressing the wireless security concern, and multiple access communications for serving as many users per area as possible. And we designed a second design that we term non-coherent orthogonal frequency division multiplexing with subcarrier power modulation, which integrates non-coherent modulation formats which guarantee low complexity, because we know that non-coherent systems get rid of the phase estimations of the receiver, and that makes from it an easier design compared to coherent systems where the estimations are very consuming. We integrate these with multidimensional OFDM modulation, which is a new direction of research where new modulation formats are being developed. It is the era after OFDM, let's say. In design 3, it's like a combination of the two above designs, where we address the spectral efficiency, as I mentioned in the beginning, per area through the multiple access design and per device through the waveform named OFDM subcarrier power modulation. I'll start with the first design and show the results that were developed in this regard. As I have mentioned, it is the integration of physical air security and multiple access. For us to dig into this design, I will start with the state of the art, what is there. And we have non-orthogonal multiple access, NOMA, which was proposed for 5G communications, among many other schemes, and it was studied extensively in the literature. In NOMA, as you can see, in the base station, the transmitted signal is sent to two users. It combines a near user and a far user. And it sends a combined signal, as you see, x1 and x2, plus x1 plus x2, with a power share allocated for each one of them. For the near user, there is less power allocated. For the far user, more power allocated, as you can see here in the power diagram here. Because the power decays with distance, so x1 needs more power. And the near user employs what is called successive interference cancellation, which cancels the dominating signal of the far user, and then it is detecting its own signal, while the far user treats the signal of the near user as mere interference and does it directly detects its signal. We can see that it's suffering from interference here, so it will degrade its performance somehow. So this is non-orthogonal multiple access. It's basic setup for two users. And there are problems with this. NOMA was, it's important to note that NOMA was proposed and studied in 3GPP, the third generation partnership project, from release 13 to release 16, and it was then removed from release 17 due to many problems. Some of the problems that NOMA has can be summarized as follows. One, constrained user superposition. So for the NOMA to work, it cannot take two users with the same distance from the base station, which is a case that can happen. So it's not working in power balanced scenarios. As you can see here, it should combine a near user and a far user. It has a complex receiver due to SIC, especially at the near user where it is performing SIC. So this is also not very good for, especially for IoT devices where low complexity is a main requirement. Also, we have seen that there is interference at the far user. So the far user does not perform SIC or anything, but it just treats the signal of X2 as mere, as like noise, because its power is very low. There are also problems related to power allocation, fairness, signaling, etc. One of the main risks is the security risk, where here, while performing SIC, this user, if it is a non-trusted user, can somehow get into the data of the other user. This is a risk, it should be addressed. And there are works that also propose the security of NOMA against external eavesdropping, where we see here if trying to decode the signals that it receives everywhere. So taking these problems into account, we propose the following design that we term multi-user auxiliary signal superposition transmission for solving these problems and being an alternative for NOMA. Where we use specifically designed signals and we superimpose them on the user's data. As you can see here in the transmitter, we are sending data from two antennas. We are combining the user's data, X1, X2, and we are superimposing on top of them some auxiliary signals, R1 and R2, that are functions of the channels, user data, and so on. And we send these two signals simultaneously. And as you can see, every receiver receives its own data, legitimate receivers, while the external eavesdropping is having problems decoding this signal because it has many unknowns with respect to him. He does not or she does not know. So this guarantees inter-user interference cancellation, where every user receives only its own data and getting rid from the internal eavesdropping risks and external eavesdropping risks as well. Let's talk about the transmitter, the internal architecture of MUAS-ST. It is simple, where we have the data of the two users, user equipment 1 and user equipment 2. It is to be noted that also these users, they don't need to be far and near users. We don't have such a constrained user superposition. So it works for any two users anywhere. It does not need to be one near the base station and one far. The data is combined, x1 plus x2, and then the specifically designed auxiliary signals are added, R1 and R2, and data is sent from two antennas, as you can see. So let's look in the design of the auxiliary signals. So when I write the auxiliary signal at the user equipment 1, we have these. So I have the signal received from antenna 1 and antenna 2, which is like the U1, the signal U1, and the channel, the U1 from here, and the channels of the channel of the user between the first user and the first antenna, and the channel between the second antenna and the first user. It's their addition, and then we end up with this expression here, where we have some channels x1 and data of x2 and some terms here R1 and R2. The same thing if I write it for at user 2, I have this signal where I have the user's data and the user channels and the noise and auxiliary signals. So how do we cancel the interference and use these auxiliary signals? If I write both received legitimate signals here, Y1 and Y2, we can see that these signals are actually can be classified into separate terms. So there is the desired terms, where I call these desired terms because this is the signal that X1 wants to receive. The first user wants to receive its own data. It does not want to receive any other thing. And user 2 wants to receive its own data with no interference and any other terms. So yeah, in the second part we have here undesired terms. So this term should be set to 0 for each one of them. And actually, if we dig into this term as well, this is actually the combination of two terms, inter-user interference. So if we look from the perspective of the first user, this is the interference caused by user 2 due to user superposition of the transmitter. But the auxiliary signals are designed in such a way, need to be designed in such a way that it cancels this term completely. And thus we can write the following equations to solve this. So I set these undesired terms to 0. And when we solve these, we get the following solution for R1 and R2. So we can see that R1 is like a function of the user's channels. It's function of X2 as well here, and R2. And R2 itself is a function of the channels and X1 and X2. From these, we can see that R1 and R2, the values are very complex. It is the combination of these channels and users' data. And this is important because this represents a real challenge for the external eavesdroppers. So it does not allow it to decode the signal. It receives mere distortion. While it cancels the interference completely for the legitimate users, as we have seen. So this is the solution. The receiver of MUAS-ST is simpler. It's nothing more than the OFDM receiver, which is adopted for 5G and 4G also communication. OFDM is important, is an important waveform that is used for all these designs. So the received data for legitimate users is decoded. The fast Fourier transform is performed, and the equalization, then the demodulation, and the data is recovered, as you can see. So it's a simple receiver, and this is important to note, especially for IoT communications, because the device is processing limited and battery limited. So carrying all the processing at the transmitter side is something that is very, very desirable. And I would like to mention that this not actually makes the transmitter also so complex because of the special design of R1 and R2. These signals are using diagonal matrices, and that's why the computational process is made faster. Let's look at the eavesdropper. So these are the steps that are encountered in receiving the signal. The external eavesdropper here is really challenging because he does not know X1, X2, R1, R2, and there is noise on top of that and the channels. So it is a real challenge. So these are the performance curves. At the left side, you see the interference of the proposed design, where these curves are all for the proposed design actually. So these are the legitimate users. You can see they have a good performance, while in all the eavesdropping scenarios there are problems. So this corresponds to external eavesdropping cases, where the external eavesdropping device, Eve, is trying to decode the legitimate user signals, and it fails in doing so. You see the performance is very degraded, and it's so in the presence of untrusted users, which is actually a problem not very positive in our case, because the R1 and R2 cancel it fully. This eavesdropping is not possible as well. So the superimposed users, no one of them can decode the data of the other. Here at the left side, we compare the performance of the proposed design with conventional power domain NOMA. So these curves at up here are for conventional NOMA, where I show near and far. So near users and far users for different power allocation scenarios. I can actually show these reallocation scenarios. I can show these because I had a small legend problem. So these are different powers given to the far user and the near user for different power cases, and for the same distance. I mean, a distance from the base station. One considered far, one considered near. We check the performance and we compare it to this curve, and we see that the proposed system is much better. So I continue. This is also the throughput of the proposed design, where we have user equipment 1 and user equipment 2 and the total throughput, while the throughput of the eavesdropping cases is degraded. Since this design is based on orthogonal frequency division multiplexing, and since this technique, even if it is the technique of choice for 4G and 5G, and many designs are now developed based on it, it has a high peak to average power ratio, and it is a real problem with it. So techniques that are based on OFDM need to be checked. Their PAPR needs to be checked so that it does not add further degradation to OFDM. And as we can see, we do not add further degradation to conventional OFDM, where MUAS-ST even achieves some lower values compared to it at some high SLR. So not to keep this short, because I am given 40 minutes, I did not include the mathematical analysis, the bit error rate analysis, and so on. But it is detailed in the thesis, and when you see these slides, you might remember some places in the thesis. So this is the legitimate users, the fading amplitude, and it is estimated. It is estimated, and then there is some approximation that is made. I would like to mention the fact that this bit error rate found here is just an approximation. So it is a theory. Whenever you want the bit error rate for specific SNR, you can find it. But the real performance is given by the performance curves shown in the simulation, because this is assuming some change in the distribution, and thus it introduces slight approximation problem, but it is still useful. So I also included the SINR analysis, which is the signal to interference plus noise ratio, and it measures the signal quality, the quality of the reception, let's say. And I have here shown the SINR for equation for the proposed design, and also for conventional NOMA, which can be found through these expressions. You know, we can write the signal of the for NOMA for the far and the near user plus some noise, and through the channels, fading channels, and then we can write the SNR according to these formulas, signal to interference plus noise, and so on. As we can see, like the performance of the SINR of MUAS-ST is very similar to the SINR of NOMA at the near user, because I am assuming user 2 is the near user, and user 2 has better performance. So the signal quality, basically, the best signal quality in NOMA is also achieved in this proposed design. I would like to conclude this design by saying that it is proposed as an alternative for current NOMA, where we claim that we solve the limitations of NOMA by providing the following point, working in general scenarios where our design is not restricted by the constrained user superposition, one far, one near. You can use it for the combination of any two users. It is also featured with low design complexity, where there is no SIC problems, and the internal and external secrecy is also not a risk. So it is perfectly secure against internal and external eavesdropping cases. And we are solving the inter-user interference problem fully through the specific design of the auxiliary signals. It is suitable for IoT devices since the receiver is just the receiver OFDM, very simple, and all the processing is carried at the transmitter. And the processing carried at the transmitter itself is easy since it uses diagonal matrices and it does not add further problems. Go to the design 2, NC-OFDM, non-coherent OFDM subcarrier power modulation, which integrates two directions of research. Non-coherent modulations, this is the aim of using non-coherent modulations in this design is to reduce the complexity of the developed design, because non-coherent systems, they don't use complex and expensive phase estimations like in coherent systems. And multidimensional OFDM modulations are used for enhancing the spectral efficiency per devices, we will see. I will first talk about the OFDM waveform. So as we can see from the upper plot, there is the other conventional multi-carrier techniques. These are not OFDM. These are different, like FDM, frequency division multiplexing. They are orthogonal also, but they are non-overlapping orthogonal. So you can see there is a spacing between each two channels, and this is somehow a waste. This is to avoid interference. But OFDM was proposed where the subcarriers are orthogonal, are overlapping orthogonal, so they enter each other, but the peaks never interfere, and this reduces the bandwidth of this kind of system, of multi-carrier systems. So it saves the bandwidth, and the bandwidth is very expensive resource. We want to serve many devices with the less spectrum we have. So this orthogonal frequency division multiplexing is one of the points why it is adopted is this. And the second is the robustness against multipath fading, which is a problem in wireless systems. So OFDM is a waveform of choice. Multidimensional OFDM formats are actually based on OFDM. So the question is, we can maybe formulate it like this. So we save bandwidth by using OFDM compared to conventional multi-carrier schemes like FDM and so on. Can we do something furthermore to also enhance the spectral efficiency by manipulating the OFDM waveform? And that is the rise of many multidimensional OFDM formats where classical modulation techniques are combined with some new dimensions for sending more data. One of the most studied in this regard is the index family, like subcarrier index modulation, modulated OFDM or OFDM with index modulation, which use the index of the transmitting of the subcarriers to convey more information bits. I would like to note that these dimensions do not devote any bandwidth specifically for this exploration. So this is a mere signal processing treatment, let's say. And there is also OFDM special modulation where the index of the transmitting antennas is used as another dimension for sending more information bits. OFDM subcarrier number modulation is also used where the the number of the active subcarriers in OFDM block is used as another dimension for sending more data. There is the gap OFDM subcarrier gap modulation, which has the same performance as OFDM-SPM, and they are developed by the same authors, I guess. And it is also exploring the gap between the active subcarriers in OFDM block. The shape of OFDM pulse shape superposition modulation is also another technique that falls under this category. So our contribution in this is the development of OFDM subcarrier power modulation. I'd like to mention that this is not the contribution of this thesis, it's rather an earlier work that was developed in our laboratory and 2 years ago, I guess. So for explaining this concept, we show FDM, which is using wide bands between the subcarriers so that they do not interfere. And there is OFDM, as we have seen, it saves the bandwidth because it uses orthogonal subcarriers, orthogonal overlapping subcarriers, very closely spaced. And then OFDM-SPM, what it does is actually exploring the amplitude or the power, exploring the power of the subcarriers in the OFDM block. It is manipulating the power level of the subcarriers, of the transmitting between subcarriers, by high and low, and thus it is through these manipulation it is sending more data. This can be understood also like this. So if we have a joint transmitted stream, normally in the conventional schemes, this is just one stream of data. But in the case of multidimensional modulations, this is embedding other dimensions. So in our case here, because we use non-coherent techniques, we have DPSK, one stream sent through DPSK and one modulated through the power levels, high and low. So to understand more about this high and low, we will talk about the power policies of OFDM. So we are showing a conventional system of OFDM subcarriers transmitting some data. And with our proposed design, it is sending some data through what we call the power saving mode. Since we can save half the bandwidth compared to conventional OFDM and half the power as well, so we can save half the power and do the same transmission as conventional OFDM does. Or we can use this saved power to enhance the reliability of the system, and that is what we call power reassignment. So these are the modes developed, the power policies developed for this design. Going very fast into the system model of non-coherent OFDM-SPM, we see the incoming data stream is split into two parts, where one is modulated through the non-coherent differential modulator, DPSK, and one through the power subcarrier modulator. And then a joint stream is formed, and it is given to conventional OFDM blocks where inverse fast Fourier transform and CP, the digital to analog conversion, etc., is done, and then it is sent. So this subcarrier power modulator is important in our case, where data is turned to values of high and low. And these values of high and low are chosen based on the policy used, the power saving policy or the power reassignment policy, as I explained. Where in the first case, this equation at the top, it shows that the average energy in the case of SPM does not go beyond that of conventional OFDM with BPSK, let's say a BPSK format, because this is a binary scheme. In the second case, the 2 in the right side denotes the fact that the power is reassigned to the subcarriers. The non-coherent differential modulator is the conventional DPSK modulator. We use binary DPSK here, and that guarantees non-coherent differential detection. So the receiver is also simple. It is just the conventional. First, the conventional operations of OFDM are done, like CP removal and FFT, and then the subcarrier power demodulator is demodulating data through a threshold, a specific design threshold. It is defined as the midpoint between the high and low levels. So when the incoming power is greater than the threshold, it is detected as a high level. When it is smaller than the threshold, it is low level. The non-coherent differential modulator does the conventional DPSK detection, where the differential symbols are decoded and biometric data is reformed again, reconstructed. So the performance of this design in the power saving mode, which is the mode where we save half of the power, this is to match the requirement of low power applications. So this mode is for the low power application. We can see that we save half the power at the expense of some degradation in the bit error rate, in the reliability. So this can be used in areas or application areas where the filter reliability is not very much a concern. While in this case it still doubles the spectral efficiency because it embeds one more dimension in the joint transmitted stream. As we can see, the throughput or the spectral efficiency of this system is double that of OFDM with DPSK. Also, the PAPR, since this is based on OFDM, we see that it does not add any degradation over it. It's almost the same PAPR, even with a slightly better at high SNR value. With the optimized power reassignment, there are two cases under the reassignment policy where we have the optimized case. In optimized case this is like an optimization problem where we allocate the saved power to the subcarriers such that the average curve is enhanced. The average is the average of the detection of the power and the DPSK. So the average curve in this case is enhanced, as we can see, and it approaches the theory or the curve of the DPSK. It is the conventional. The upper curves are the proposed, and the down is the conventional. Also, the throughput in this case, the spectral efficiency is doubled, as we can see. The PAPR is much better than the power saving mode. It is also better than OFDM. There is another power reassignment that we designed specifically in this thesis. The other two were based on some earlier works, but this case is specifically designed in the scope of this thesis where we are having a non-coherent design. So NC-OFDM is non-coherent, and we know that non-coherent systems perform worse than coherent systems, but they are simpler because they don't use expensive phase estimation and so on. They get rid of the phase estimation. And on the other part, we have coherent systems. They are better in performance, but they are much complex. So since we are having a modulation format here that is two-dimensional, not like the conventional modulations where we have one fixed curve, we use this flexibility of the MUAS-SPM so that we solve this classical problem in the literature, where this classical trade-off, let's say, between coherent and non-coherent systems, where being a non-coherent design, we can design OFDM and NC-OFDM-SPM to achieve the performance of coherent modulations. So at the same time, you combine the benefits. And we are doing this with the following system. This optimization is defined as where the DPSK stream is set to match the performance of coherent OFDM with DPSK, while we set the power stream constraint free, so that it allows a degree of freedom in the optimization. So we can see here from this the figure below that we have the performance of the proposed system, which are the red curves, are matching the performance of coherent OFDM with DPSK, while this has some impact on the power curve. As you say, this black curve is much degraded than the others. These can be allocated for a user application where reliability is not a is not very important, maybe. And we can see that we pass the performance of OFDM with DPSK, the non-coherent OFDM, which is the squared curve, and we match the performance of coherent OFDM. This means that with this policy, NC-OFDM-SPM is a design that combines the merits of coherent systems and non-coherent systems. Being a non-coherent design ensures low complexity, and achieving the same performance as coherent OFDM with DPSK also makes it very good in performance. We can see here the error which is related with this system, where we see that it is very, very negligible. The curve attains the performance of coherent OFDM with BPSK with a very, very negligible error under 3% and even under 1% for most cases. So these are the throughput simulations in this case, as I have shown, and this is the PAPR also, as we have shown. It does not add any degradation over OFDM. This is important. The mathematical analysis, I detailed it in the thesis, but I just keep some snapshots from it here. So there is the derivation of the DPSK stream, which is based on this. We can think of it based on the differential of the DPSK because we are using it as the modulation here. So we can think of the power levels making some change in the Euclidean distance between the symbols in this case, and we have shown that the performance is like this in the thesis. For the power stream, the same thing. There are two transitions that are related with the detection, the erroneous detection of the power levels. One is like when a high power is turned to a low power, or a low turned to high. And we have detailed this, so if you have any questions regarding this, we can I can try to answer them. In the conclusion, I would like to say that this design is featured with the special merit of doubling the spectral efficiency per receiving device due to the use of multidimensional OFDM modulations through OFDM subcarrier power modulation. So it doubles this, and this is important because we have devices that are really data hungry, and this needs to be served. It is featured with a simple receiver design due to the non-coherence property, where it is using two non-coherent demodulators, one the non-coherent differential demodulator and the threshold-based demodulator also. It does not use the phase estimations and so on. It is also low power because in the power saving mode, let's say, where yeah, as I explained, it's achieving coherent performance in the case of in the last case I explained, where it can be designed to achieve coherent performance. No PAPR degradation. This is important for OFDM. So I would like to go in the design 3, which we term as DC, doubling the spectral efficiency per area and per device, where we combine these two designs some way. Not exactly. So this picture can show us the how to enhance the spectral efficiency, or the categories of spectral efficiency, as I explained in the beginning of the presentation, where one type of enhancement of the spectral efficiency is the enhancing the spectral efficiency per area, and this is through the use of non-orthogonal multiple access, MIMO schemes, and so on. But NOMA has proven non-orthogonal multiple access designs. This is proven that it is a good choice for this kind of, where a lot of users in an area can be addressed at the same time. This is a solution for the spectrum shortage problem, rather than the other. There are some other takes on for solving this problem, such as millimeter waves and in-band food duplex and so on. But these have their own drawbacks. I show here with this arrow that the spectral efficiency per device also can be enhanced through the use of multidimensional OFDM modulations. And in this case, I showed OFDM with subcarrier power modulation, where we see that the transmitted stream, in the transmitted stream, there are two other dimensions that are embedded, and then this carries just more than one stream, carries two streams of data. So the transmitter design is also simple, not complex. It is just like the transmitter of NC-OFDM that I've shown. There is the SPM modulator, subcarrier power modulator, where the high and low levels are designed, and there is a power of it that is outputted, power sequence that is outputted. And there is a BPSK modulator. In this design, we use BPSK for both the SPM part and also the multiple access part. So it is somehow a combination or integration of the MUAS-ST that we developed in the first design and the second design, but this is a coherent version of the second design. So it's using binary phase shift keying, not DPSK. So there is the binary beats, and then the joint stream is formed as the addition of the So a joint stream is formed for user 1 and for user 2. So this ensures doubling the spectral efficiency at each user. And then the superposition ensures serving 2 users per area. So this is where the name came from, doubling spectral efficiency per area per device. And same as MUAS-ST, in the first design, the superimposed data is designed with the auxiliary signals to cancel the interference and solve the security risk and so on. The receiver is not very complex. The only different part is this part. So it is same as OFDM receiver, where at the end the SPM receiver is used because we need to detect the BPSK bit and the power bits. And they are, as I explained, in the part of NC-OFDM-SPM. Just in this case, BPSK is used instead of DPSK. So we can see that also the external eavesdropper here is challenged because he does not know the data as we have seen for X1, X2, and R1, R2, and the channels. And more than these, also in this case, there is the joint stream X1 and X2 is formed as the binary bit stream and the power bit stream. So he needs also to decode that. So there are levels of complexity that he's struggling with. Yeah, this is the transmitter for the legitimate and illegitimate users. The performance is as follows, where we can see the curves for the proposed design here in the left, where there is the power stream, the BPSK stream, and the average stream, which is the average of both streams. For user 1 and user 2 are the legitimate users, and they, as I said, they don't need to be at any distance from the base station. They can be at any distance from the base station. So here we have it also. We have the performance with the eavesdropping cases. So we have the eavesdropping scenarios above, where we have external eavesdropping cases and internal eavesdropping cases. And we see that the legitimate performance is good, while the eavesdropping cases are suffering. So there is the spectral efficiency performance here also, where we can see that it is doubled for per device. So each user has its performance doubled, user equipment 1 and user equipment 2, where I specified by both. And then the spectral efficiency of the overall is doubled. This 4 means that it is doubled per device and per area. The PAPR also is plotted on the right, where we can see that the PAPR is much better than conventional OFDM with BPSK. In the conclusion, this design is developed as a combination of the two mentioned in the beginning, and it is a solution for the spectral efficiency per a given area and per also data-hungry devices. So it is doubling the spectral efficiency at the user level, the device level, and also at the multiple access level. There are no security risks in these cases, since it is using auxiliary signals design, where the signals are very designed, specifically designed to solve the interference problem and solve the external and internal security risk. Interference mitigation, as I explained. So this is all about the ideas. Out of these, we have, as Professor Jihad highlighted, we have written some papers, some published journal papers. We have here 5 published papers, and we have 1 paper that is under we are preparing it for submission to IEEE. So I have some patent applications for these 3 designs that are developed in this thesis. And at the end, I would like to thank all of you for attending my defense, specifically the jury. I thank you so much for being part of this. Professor Jihad, at the beginning, you are thank you so much, and this is the end. Thank you, everybody.
Thank you, Abba, for your presentation and for the contributions you have explained to us. Now we can move to the question part. Please keep your presentation shared so that the thesis committee member can ask you to move to any slide they want. We can start with Dr. Deniz Hoja, the internal committee member, if he has any questions, if he any comments, any feedback.
Okay, so can you hear me?
Yes, we can.
Okay, good. Thanks for the nice presentation. That was a very good presentation, and the work is really nice. It's well done. I have a small couple of minor questions just to better understand the topic. So I think it was somewhere around slide number 10 or something after the, let me see, where you show an equalizer for the first time in the receiver part.
Slide 10, you said?
Yeah, go ahead a little bit more. Bit more. Okay, here. So there's also equalizers in other parts of the presentation. So my question is, could you please define what an equalizer is and what type of equalization is done in this receiver here?
So we assume the knowledge of the, because this design is a coherent design, so it is making phase estimation, and we assume the knowledge of the channel. So it's just dividing by the channel, the effective channel actually, to get rid of this. So when I show here that the signal is received, for example, for user 1 and user 2, which are the legitimate users, we have a channel here, H11 and H12. And we need to know these so that we divide by it to only receive the data itself, X1 and X2. This is what I mean by equalization in this.